In early 2026, the global computing baseline flipped. Inference, the workload that actually serves users and makes decisions, surpassed training to consume over two-thirds of all global AI compute. That production workload looks completely different from the simple chat interfaces of a few years ago. We are no longer making single API calls to a single massive model. Consider a realistic enterprise deployment. A bank needs to process a 200-page regulatory filing. They deploy an agent mesh. This is an architecture where multiple specialized models, a researcher, a fact-checker, an auditor, and a writer, run concurrently to analyze the exact same source document. These agents operate simultaneously. They share context. They must hand off intermediate states to one another in real time to form a complete output. Enterprise AI operates as a distributed system. Serving these workloads require hardware engineered specifically to handle intense, interactive concurrency. The industry standard for AI compute is the NVIDIA H100. The H100's memory and compute pipelines are optimized for tensor parallelism. They are designed to split one massive training model across multiple chips, rather than routing state exchanges between multiple different active models. When you map a 4-agent financial mesh onto the H100, the hardware constraints immediately surface. You are forcing 4 separate model contexts into a pipeline built for one. To manage this, the system relies on CUDA MPS. CUDA MPS is the software scheduling layer that allows multiple processes to share a single GPU. Once you reach roughly 8 concurrent contexts, the hardware gridlocks, constantly swapping memory states to keep the agents running. Every time one agent hands off its work to another, it transfers its key value cache, the memory footprint of its previous token calculations. Without hardware routing support, this massive cache must be serialized and pushed across the PCIe bus connecting the GPU to the host system. That software-scheduled trip across the PCIe bus takes between 50 and 200 milliseconds per handoff. For a multi-agent system exchanging data hundreds of times per second, those milliseconds compound. Software emulation of context switching destroys throughput, proving general-purpose GPUs are structurally misaligned with agent mesh inference. If inter-agent handoff is the primary bottleneck, the solution cannot exist in software. It must be etched into the silicon logic itself. This is the Cortex chip. Its core innovation is the Cortex Mesh Fabric Controller, or CMFC. This is a dedicated hardware block that operates as an inter-agent scheduler built directly into the silicon. The CMFC's context slot manager natively maintains 256 independent agent contexts, each with an isolated memory space. Upon finishing a task, the state transfer engine moves a 32 kilobyte cache block directly between slots using DMA, a hardware protocol moving data without the main processor. Because this transfer happens on the chip's internal fabric, it completely bypasses the host CPU, the software scheduler, and the PCIe bus. Inter-agent handoff latency drops from 50 milliseconds on a GPU to under 2 milliseconds on Cortex chip. The CMFC treats AI agents like a traditional CPU treats parallel threads, removing software routing penalties to let 256 agents execute concurrently without gridlock. Moving the data faster solves the routing problem. But GPU clusters also force multi-agent systems to perform massive amounts of redundant memory allocation. On a GPU, 4 agents processing the same 200-page document independently compute the exact same context. This creates 4 separate 21 gigabyte memory blocks, 84 gigabytes consumed for one document. Software workarounds require constant synchronization, and the first agent still pays the full compute cost. The Cortex chip solves this with a shared read bus. When a document is loaded, hardware marks it as a shared read region. All 4 agents access the exact same 21 gigabyte block simultaneously through hardware-level broadcast coherency. One computation serves all 4 models. For a standard 4-agent pipeline, 75% of the redundant compute is automatically eliminated. By managing shared memory in silicon instead of software, physical memory constraints are converted into raw throughput capacity for the entire mesh. There is an entrenched assumption in AI hardware design. Competitive chips require the most advanced, expensive 5-nanometer process nodes. This roofline model chart plots performance limits. It shows that transformer inference is strictly memory bandwidth bound. The workload slams into the horizontal memory bandwidth ceiling, long before it can utilize the diagonal peak of raw compute flops. Shrinking to 5 nanometers adds massive compute logic, but those arithmetic units sit completely idle during inference, starved while waiting for weights from memory. The industry standard for enterprise inference is now W4A8 quantization. This technique compresses neural network weights down to 4 bits and activations to 8 bits, reducing memory size while keeping accuracy drops under a strict 2% threshold for enterprise tasks. W4A8 compresses a 70 billion parameter model's weights from 140 gigabytes down to 35 gigabytes, reducing the required memory bandwidth to roughly 250 gigabytes per second. Cortex chip's standard GDDR7 memory delivers 1.8 terabytes per second, clearing this requirement with massive headroom. Pairing expensive 5 nanometer logic with rare memory packaging for quantized inference is mathematical overkill. A mature 12 nanometer architecture maximizes hardware utilization without absorbing hundreds of millions in engineering costs. That combination of 12 nanometer logic and standard memory scales into a commanding rack-level economic advantage. This image shows the infrastructure footprint required for the incumbent baseline. Running a 256-agent mesh demands 32 H100 GPUs, costing nearly $1 million and drawing 22,400 watts of power. CortexPod handles that exact concurrent mesh capacity on a single $3,000 chip, drawing 300 watts. But the cost is only half the problem. Under the January 2025 U.S. AI diffusion rule, Asian markets like Vietnam and India are subject to strict volume-capped export controls. The regulatory choke point for these restrictions is CoWoS, chip on wafer on substrate. This is TSMC's proprietary advanced packaging technology required for high-end GPUs. If a chip needs CoWoS, its distribution is controlled. By utilizing standard packaging on established 12 nanometer nodes from global foundries and Samsung, the Cortex chip entirely bypasses the TSMC CoWoS bottleneck. The 12 nanometer specification bypasses export quotas by design, providing reliable supply chain access to constrained markets. That hardware accessibility collides with a massive regulatory shift. Throughout Asia, data sovereignty laws like Vietnam's Decree 13 and Singapore's compliance guidelines are taking effect. These mandates legally disqualify Tier 1 financial and healthcare institutions from routing their sensitive enterprise data through centralized hyperscaler APIs. India's DPDP Act expands the scale of this requirement across one of the fastest-growing AI markets in the world. For these heavily regulated sectors, running inference locally on hardware they physically control is a strict compliance mandate, not a preference. The infrastructure gap to serve this mandate is critical, and the window to establish that hardware footprint is closing between 2025 and 2027. The era of the single AI oracle is over. As enterprise deployments fracture into distributed agent meshes, serving those workloads requires hardware compiled natively for concurrency. And scaling that hardware requires true supply chain independence.